Okay, this is video about hydration of an alkene. Okay, and I'm going to use molecular models in order to demonstrate this. It's out of the Timberlake book that I've been working with. It's on chemistry, organic, and biochemistry. And the example is going to be hydration of ethene. Okay, it's got a single double bond. And I'll just briefly go through this. In the presence of a catalyst, which in this case is H2SO4, the water molecule reacts to form ethanol. Okay, the double bond is broken, and the single bond is formed, and an alcohol is the result. Okay, this book doesn't go through the reaction mechanism. Okay. And that's what my objective is to use the chemical kit to show the mechanism, okay? So here's what we have. We have H2SO4 molecule over here now. An H2SO4 molecule, you can't really do accurately with the chem kit, okay? Because the sulfur has got octahedral bonding symmetry, but in this case, because of the double bonds, it'll be to first order a tetrahedral. It's going to be AX4. Now, the actual molecule has bond angles that differ from 109.5. It's not actually tetrahedral, okay, but that's what we use with the VSPR theory. Now, so this is just representative in order to make something which is, as good a job as I can get with the octahedral kit. I put the two double bonds in these adjacent positions. And you get something which is, a distorted tetrahedron, okay? So that's starting material, H2SO4. I've got some water, because it's taking place in aqueous, and I've got the ethene with the double bond right over here. Now, H2SO4 is a strong acid, okay? So it's essentially going to be 100% ionized. And the hydrogen ion is going to be bonded in a hydronium ion, okay? Now, the chem kit doesn't allow us to bond a hydronium ion, okay? The oxygen just has two. So what I'm going to do in this particular case is I would just put that next to it, okay? Showing that it may be weakly bonded. The reality is, I'm sure the H3O is, it's a symmetrical bonding between all three. So once again, it is just representative of what's happening, okay? Now, the idea here is that the pi bond in the double bond is a nucleophile, okay? It will attract, it's a positive charge, okay? Once again, in the chem kit, the double bond is shown like this, but in the reality, there'll be a sigma bond and a pi bond. The pi bond will be sticking out in this direction, and therefore, that's where there can be an attack, okay? And the electrophile, in this case, is going to be the hydronium. It's going to be the positive hydrogen ion. This is positive, this whole this has a +1 charge, okay? The corresponding balance charge is over here, and we're going to show how this will react. Now, the idea is that in a step-by-step manner, the hydrogen here can attack the pi bond, okay, forming this type of a structure, okay? And this now is a carbocation over here, okay? This is carbon +4, but there are only 3 electrons that it's sharing, okay? This is a +1, that's the carbocation. This, on the other hand, is going to be a sigma minus, okay? And that will be a candidate for the final attraction now between the carbocation, which will be a nucleophile. I'm sorry, it will be the electrophile. this is negatively charged now, and this will be the electrophile. So this is going to form an intermediate, okay? And this intermediate now is subject to a deprotonation, okay? This overall is going to have that a net positive charge, okay? And the deprotonation will take place in a way that water, now you might say the original sulfuric ion could also attract back this hydrogen proton, okay? But the idea is that the water is much more numerous, even though, so the probability of this making that will be smaller, and the deprotonation would take place like in a way like this. This proton now is lost, and this bond is now formed. This is now a neutral molecule. This is stable, and you'll notice this is really back to the starting position, okay? The H3O. This, of course, could go back here, but because this is fully ionized, that doesn't happen very frequently, and mostly that this is going to be in the form of the H3O and the HSO4 minus 1. And in this case, we have ethanol, okay? And I won't bother to change the bond lengths on these, okay? Because as this, molecule finally stabilizes, those bond lengths will adjust. The original bond lengths in the kit are not necessarily accurate anyway, okay? So there is a step-by-step for hydration of ethene into form ethanol, okay? Thanks.